Welcome, friends. Thanks for stopping by. Today's video is a little bit of a mixed bag. The general theme is the wrap-up of the Phoenix build with changes and modifications made along the way. We start out the video with a quick engine test, and at the end we talk a little about upcoming video series on the aluminum 24mm engine build, which is the next series. Enjoy and visit my friends at Rotary Rocketry channel. They do a more in-depth construction of PVC engines and rockets on their videos. Also, the Rocketeer gives some valuable information on his channel. Maybe one of the most detailed series of videos is over at Tech Ingredients. The links are provided below.
The one thing I did about it is this one has the ejection charges in it already. Is this size of rocket and the weight that these fins are just not big enough. So now take these fins and increase them by the percentage that this rocket is different. And I really need to increase the length of it, but I'm trying to keep the weight down to some reasonable figure. On this one, the body would be yeah, I'm gonna need some glasses, read that ruler. Bad be old and blind. And I can see good, I can drive without glasses. But anything up close, I can't see it for crap. So it's 33 inches long, just the body part of it. So what we're gonna do is increase the length on this one and gonna increase the fin area to be in line with this one. So it's kind of going to be an upsized Big Bertha. Big Bertha. Big Bertha. How many times can you say big? Okay, so then we got to figure out what percentage that is. Again, I will need my trusty glasses. This one is a 2.7 on the outside, and this is a 3.2. And that gives me a 16% size difference. So if I take the 33, this stupid calculator has not got an easy percent on it, times 0.16 plus the original 33 is 38.28. So let's make it 38. And this one is 32, so it needs to grow by 6 inches. And that shouldn't add a lot of weight, 6 inches to it. On this rocket here, don't even have this has got a 1/4 inch rod for lunch slug on it. I normally fly this, and if I fly it here, I've flown it here a few times on a F-24. And I put a Jolly Logic on it so that I can get it back down to a reasonable altitude before the parachute opens. Can't say enough good about Jolly Logic. Their device works every time, just the way it should. This one, and I'll cover a little bit of the differences in the one I built on the Phoenix series and this one, and also talk about the changeover. This one, as you can see, has got the smaller fin attachments. Same thing, it's got 3 rings inside, And since I made a longer engine, I had to put an extension on the back of it for this particular rocket. The two glued on rail lugs, the better fins with the word Phoenix written on it, and just a standard nose cone. I don't have a parachute on this one yet, but it's just a basic nose cone with some weight up in the front of it. It's about that far down. It's cement, so I add some weight up front. And when I add it's already at 1.75, I think, stability. But move it out 6 inches will probably bring it up to around 2 easy. What I did is I was going to put screws in this mid mount because it's dual deploy. I wanted to do it from the center section, which makes the most sense to me. Yeah, but it could have been further up, with a longer rear end on it. But anyway, this front piece would have ejected. The first part, in my opinion, would be, a lot of people do it the other way around, but the first part for dual deploy is the bottom. And then the main would come out the top. And that's true for this rocket, except the division point is right here, close to the center of gravity. So, what I did, I was going to put screws in it. And let me tell you, after working 3 days on FreeCAD, Blender, I never was able to get screws. They come out fine on the design, they look good, but when you print them and try to screw them down together, they bind up, and I make them smaller, blunter, more space. Nothing ever worked for me. It's something I don't understand. So I finally gave up on that, and I said, well, you know what, I'll just put a bayonet mount on it. So what we got here is this piece would come out on the first ejection, and I don't have a parachute here now on this bottom piece, and I probably won't put one because all it does for me is it makes the rocket non-ballistic. So now it's kind of falling in a tumbling, almost sideways arrangement, and this centerpiece is screwed to the top section. So when the top section deploys this parachute, it would pop the nose cone off. So what I did was just put a bayonet mount in there, and this flight computer would have some foam in it. It's not ready to fly, obviously, but that lets me get to it there and put the battery in it before we fly it and connect the two pieces together. Hopefully there'll not be enough rotational force to undo that bayonet mount. If I do, it's going to be quite a show in the air. So the flight computer, this is an old one. It's got the new software on it, but it's an old board that's been around for a while. So I've had such bad luck of losing these rockets that I want to put something new in it. The new one is quite a bit smaller. And this is the one that we'll be building as a kit. And so it's about a 50 by 60 millimeters, but it would fit in here very easily with a lot of free room for packing or however you want to mount it in there. So to put it back together, it's just a simple matter of lining it in there where it will not interfere with it, but then it's just a simple twist motion and it's ready to fly, just like that. So we're going to take the measurements on these fins and then increase it by 16%, which will add a lot of distance away from the body. And to do that, when you're using open rocket, you have to put the coordinates of the fin where it bends at. So I'm going to start here on the body, and that will be the X point. And this would be the Y point. So I'm just going to round it. It's 6 inches. So it's 6 inches on the base. The high point is 2.5, and it comes about a 1/2 inch before the body tube. So this would be the aft end. The high point's going to be about a 1/2 inch, which, what did I say it was? 1.75, and then the run back is 5. Be 5.8 inches. And 5.75. You make this one 5.75. You make this one 6.4. .75 and 7 inches. So that's got all that. I increased the length on this one to 38 on this one here, and increase the fin size. The body size, the body diameter is already fixed at 3 inches. Nose cone will be pretty close to an increase, maybe a little bit big on it. Add some weight to it and maybe get a little more stability. I increased the lunch rod from 6 feet to 10 feet and rebuilt it. It got a little wobble to it from engines exploding, and so that's what we'll do on the Mark IV as it is. I don't handle things jumping on me from the back very well. They normally get slung or flung onto whoever's closest to me. And then I'll look for them. If it's something needs squishing, I squish it. There. Well, that's not only all I know today, that's about all I know, period. And I may not make a parachute for these. This one's got a commercial parachute in it. But every time I fly it, I'm able to recover it. These have been one-trick ponies, and I may just use like a giant streamer or something. Something I don't care to lose. I'm tired of making parachutes and them hanging to the tops of trees. So I don't care if it breaks a fin on the way back down, if it at least can recover the rocket. This is a different size plywood too. This is not a quarter, it's a 1/20 of an inch. 0.20 inches. So it makes it a little bit lighter. But to me, that comparing the two, these fins versus these fins, when I look at the size difference, I realize these fins are just really not big enough for this size rocket. And that's why it's got to be going at least 30 feet per second off the rod versus 20. And you know, these big Berthas are slow flyers anyway, so got a lot of wind resistance. Okay, we're going to be building the Mark IV here is the continual part of the last part of this series on the Phoenix. And you can see that the first fin has been installed, and this is the style fin it would be. It's kind of a copy of a Big Bertha expanded. The rocket will be, I think, 39 from the end, that end to this end. It'll be 39 inches. This one is a 3-inch tube, and it's 27 inches. The fin extends past it by about 5 inches, 4 inches. So you can add 4 inches to the 27, and that's the length of this part of it. And this part is 12 inches without the nose cone. The nose cone's about 6. This middle section here is not going to add to the length or take away from the length. It will be fastened up here into this section with the parachute. Good grief. Where'd all that come from? Anyway, the parachute and the protection cloth that goes with the parachute and the shock cord and so forth will be in that end. And this is fastened with this is a dual deploy 3D printed device. And so it's a bayonet mount, just undoes like that. It will have 3 holes in it, one for the wire extended down to the drogue. And on these rockets, all I'm doing is on the drogue. These are expendable rockets. I don't go to a lot of trouble to make them long lasting like I would a normal build, because they're still experimental. The engine and the rocket combination is experimental. So you got these 2 pieces here. There'll be 3 holes in this one, 3 holes in that, 2 holes to attach the parachute to either end of it, and it will sit right in the middle of the rocket. And as you can see, I had to change filament. I ran out of the white and switched over to some colored filament. But to put it together, it's just a simple twist and turn. Now we don't want the rocket twisting, so I'm putting straight fins on. A lot of times I'll use 6 degrees on the fins to give it a spiraling ascent. In this particular case, we're not going to do that. And so then this flight computer that I just built is minus these test circuits. The advantage of having it sit in the middle is that the wiring is all interior and it's very compact. So like I said, there'd be a wire running out the bottom going to the drogue. I'm not calling it a chute, but it's not. It's just it's going to kick the back end of the rocket off, make it very unstable. And then the main parachute is in the nose cone section up here. So you can see this device is sitting right between the 2, and it gives it access to the ejection charges. So what I do to mount this thing is I'm just going to take a piece of foam rubber, because this device is not indestructible, but it's very capable of taking care of itself in normal flights. Then the battery would just go down in between here like this. It would be plugged in and it would be inside there. The wires extending out of this would already be attached, and all that's required is put the ejection charge on it, so it just goes just like that. And at the end of the flight, this one is permanently mounted, more or less, not permanently, but it is screw mounted in here. It don't come out. And the wire would be long enough to pull the ejection charge out the top and replace it without taking this thing out. And the one out the bottom obviously don't have a parachute or anything to worry about, so we just would undo the rocket like that, put the new ejection charges in it, and fasten it back. So that's one big change. Printed nose cone, just a basic dusty nose cone. It keeps blowing dust out every time I open it. And a good solid bar across it. Just jack, to mount the shock cord and the parachute and all off this cone. Some of these cones I use the same Rockcrete that we build the engines with. I'll put it right up in the nose cone, and when I 3D print these, I use the tree support on it. And of course, this center section has to be supported off the 3D printer plate. And I leave a portion of it in there so I can pour the cement in, and it's got an attachment point. Kind of give it a little extra ability to stay in the top and not come crashing down through the bottom. And it's a little loose, so it would have to be tightened up. It's got my phone number on it, in case anybody wants to recover it. And then on the exterior of the rocket right here would be a printed tag that's got the network ID number, so I know that it's talking to this rocket. So I know my cell phone is talking to this rocket, I should say. So that is that. And we got fin number 1 attached down there. See the hot shot straight up down doodad. So this thing comes off more or less. Right now, mostly less. And then the flue fillet will be along the length of the fin here. And inside, about halfway through, is the centering ring. That's far enough down to grip the top of this engine as it goes in. Keep it from moving against the thrust plate so it can't change directions, get over one side or the other. And then there's one in the back that it would go through. And this would be just, there's no ejection charge again. This is just a friction fit inside those rings to keep acceleration and G-forces from kicking it out and losing the engine. Not that it's not even good anyway. Once it's burned, that's the end of it. So I'm gonna go ahead and show you how I mount these now, which is the same as the other rocket. It's just that you have to decide where the back end is right there. And I'm gonna mark this ring so I know where to cut it. And then bring it back to the back part. I'm gonna widen it out just a little bit. So we got that on there. We'll come up about this high and come down so it gets a good grip on that ring in there to secure it fore and aft. That area is so small, so tight right there that I don't want to risk breaking my skill saw's blade. So what I do is just cut from side to side with my trusty compadre here on both sides of it. And I'm going to count on these long nose pliers. Then we'll just snap that out. And right out of there. Leaves a little bit in the center, but that's not a problem. Alright, so then we're going to fit this down on there like that. Going to bring it to the back, and we're going to glue that one in. Got a lot of rubber bands on there. I don't want them obviously do not want them under the fin. That would not work well. And this fin was like the key fin. I can print on a 12 by 12 piece of this 1/20th plywood. I can get 3 of these because they're larger than the other ones were. And this little guy here, he had the cross piece, the center of that piece of wood. And that's another thing I've changed, which I shouldn't even have to done it to start with. I would measure the width and the height and then divide it in half and then wind up with a cross, not an X, but a plus sign in the middle of the wood, which signified the center. And so I changed that to just going corner to corner, 2 different directions, and so where they cross, that's a new center. That's the center. That's where your diagram out of easel matches up with what's going to print on the piece of wood, or not print, but cut. Got 3D printing on mine, I reckon. I put a pretty good gob of glue on there. Just and then I'll plant that right there. Oh, don't you give me any problems now. We done tried you and you fit on there. There you go. You knew fixing to have problems. Get this stupid thing glued on there again. I know about it. Take this Q-tip and get rid of some of that glue. I don't want it on that fixture. Makes it hard to get it off. We're going to put one rubber band on the fixture. One rubber band's going to come up and get on the fin. And then the last rubber band is going to get on the back of the fin. I may have lied to you because as I get the fins on there, I can't really get that back one on there. So this guy here will have to do double duty. So what I'm looking for now is that fin is canted pretty good over to one side, you know, about 12, 15 degrees angle. That obviously is not going to work at all, ever. Now we bring him back up straight. And I just look down the tube and make sure that it's square away from the tube and that it's fully seated and that it's all the way back to this edge, that's my mark, and that it's down on the tube, not standing up. And one last check, is it straight? Well, tell you the truth, right now, only me knows where it's straight or not. But it is straight. Now I gotta find something sticking in this tube, keep it falling off the thing while that glue dries. Oh, you wanna act like some kind of fool now, don't you wanna roll over? We don't tolerate that. And instead of a 3-fin, this is a 4-fin rocket. Try to get it stable where we get a straight vertical flight out of it. And that's it for today. Once that fin dries, we'll march on down the road to a new location with all 4 fins on it, and then start putting these fin guides on there. I got the question whether I'm gonna use these or not. I think I will. And they really need to be put on before the fillet, or as the fillet of glue is ran. Otherwise, they would have to be sanded out. Ever how high that fillet of glue is how much would have to come off this corner piece here. It wouldn't take long before you would lose your 90-degree angle. Okay, so here we are today. We're going to put the hole in the end of the end cap. The easiest way I found to do it is just center it up on the chuck here. We're going to expand the jaws to hold it. Shut that, turn it on, rev it up, and go right straight through the center. And it's done. Centered, right size. Then you take it off the chuck, and it falls down in there with all that aluminum trash that's in there. Let's see if we can't get a little better angle on it. Yeah, there we go. So we center him up on the chuck. Rev it up. Drive the bit through. Made a lot of them this way. Sure, somebody will find something wrong. I am not a machinist. Never claimed to be one. I got enough sense to turn the machine on and off and keep my finger out of it, so I guess that semi-qualifies me to be a machinist. Maybe. Run this through. Well, I'm gonna make them 3 today. 3 120 millimeters by about 115 grams of standard sugar fuel. And that, as they say, is the way I do that. And drop it every time. See, you got a nice hole there right in the center, all the way through. Without a whole lot of problems. You never leave the chuck in a lathe machine. Turn the lathe off. Get rid of some of this garbage in here. Ready for the next one. Okay, welcome to the wrap-up on the building of the Phoenix. This is going to be going over some of the changes I made along the way. Since I built that, it was a Mark I, I think. And the one I'm going to show you here at the end is a Mark IV, which I'm just, you know, you call it serial number 1, 2, 4, or whatever you want to call it. However, it's the 4th generation. So the fins wound up being mounted with these tabs here, these supports glued to the tube, which works out, I think, really well. Gives a lot of extra support to the fins. And you got to remember that as I'm building these are not competition showcase rockets. They're research, and so far it's been pretty much one and done. So I'm not worried about the paint or really the appearance that much. So you got 2 glued on guide rails here. for the 1010. I initially put the flight computer in the nose cone. It's a really good location for it because it moves a significant amount of the weight, a couple ounces forward, which is always what you want with a rocket to get a good balance point. But since then, when you do that, you can have one interior rod for this main parachute deployment, but then you have to have an exterior rod or another interior rod running down to do the drogue. And these particular rockets do not have a chute in the bottom. My goal here is to fly low and do a fast recovery so I can stay within the confines of the field. So basically it's just going to kick the back end off. I think this one actually did wind up with some kind of small parachute, a 12-inch one. But most of my build is just, no parachute at all for the drogue. It kicks off the back so you don't get a ballistic descent. It's kind of falling sideways and spinning and slowing down enough that then we can deploy the main. And then the ejection charge is just loosely packed in the bottom, especially because it's not got anything. So then the flight computer is inside this centerpiece. And this one appears to be all one piece. I don't see any real connection point on it. So other than what I was building in the video, this is the only two changes, significant changes made to this rocket. Now I'm going to talk about this one for a second. This is ST's Big Bertha for it likes an E18 Aerotech or F-24 is a good flight on it, or F-20 commercial engines. And this would be a rocket that would be flown at one of my club launches. So initially when I started with the Phoenix, I didn't intend to copy this, but the more I worked on it, the more I realized that maybe subconsciously I was copying this rocket. And this one's flown with a Jolly Logic. So then we go to the fore here. And in an effort to copy the Big Bertha, the fin's got a longer sweep on the aft end of it. They got more area built up. Same two rail mounts here. The nose cone is 3D printed with varying color silky. And then in the center is the same arrangement we had on the other one, which is no parachute in the bottom. So it's going to kick off this. It's going to kick off this back end as the first deployment at apogee. And the next thing that's going to happen is, set that down there, it would kick off the nose cone and the main chute at predetermined altitude. And that's completely adjustable with this flight computer that I'm flying. So then inside here, you will see, maybe if I can get enough free space here, the flight computer is just wrapped in a piece of foam, kind of protecting it from a nose-in landing. The flight computer is very durable. It don't need a lot of protection. And the opening for the flight computer, and this is a bayonet mount, not a screw mount, this is bayonet. And so the opening for the air pressure is here, about a half-inch hole right there. And I'm going to put I'm a little worried about when this thing is spinning around, it's going to disconnect this bayonet. So I'm going to put one locking screw in there before it flies. It'll just have one screw that would lock these two pieces together so they can't unscrew in flight. Not up flight they're not, but when that thing is spinning around, it very well could undo the bayonet, and that's not what we want. And then this side here is the main parachute, and right below it is the ejection charge, flight computer, just a blank nose cone with a little bit of weight added to the front of it. And the balance point is somewhere I marked it with an E. Yeah, the balance point's right here. That the E signifies no engine. And then the software Open Rocket will add the weight of the engine when it's added to it. And it's given about 800 to 1,000 feet projected. And hopefully it will be a straight up and a straight down flight. Well, the problem I've been having is probably low engine power because I took Rotary Rocketry's engine and copied it, but then modified it. And I've had a lot of issues with, initially it was weak potassium nitrate, and then later it was end caps. These end caps here, even though they say they're Schedule 40, they are not. They will not stand up. And so if this end cap is mounted on the upper end of the engine, it's been exploded. So the modification to the engine is to lengthen it to 120 millimeters, the pipe. And it's got 115, 114 grams of fuel in it with a 3/4 inch core. Again, copying Rotary Rocketry's latest smaller engine. And I think he calls it the Dark Monkey. I'm not sure I remember that exactly. But anyway, he's got a video on it if you want to see it. And so this is pretty much just a straight copy with a number 18 washer as the nozzle end of it. You can see this one's been burnt and it burns out the cement, but the engine held together good, and it came out to be a G70. The first ones were built with a shorter engine, which is 4 inches on this one, I think. 4 inches, and then they increased it to 120 millimeters on this one. And the millimeters is a lot easier to keep track of for me. And also on the fin, on the first video, you seen the CNC machine cutting the fins, and so I had to make a couple little changes. I went to a lighter plywood. This is a 1/20th inch or a 0.21 inch thickness. It's not a 1/4 inch, so it's a 0.04 difference. And I changed the Phoenix to have a little different design on it. And since I increased the size of the fins, I was getting 4 out of a sheet of plywood. Now I can only get 3. And I may even have to cut it down to where I only get 2 if those fins are not big enough. You don't want to make the fins too big. You get a lot of drag when they're really big. Again, a 3D printed nose cone out of the varying colors, which makes an attractive nose cone for a rocket that's going to be painted and made to look good. And then the center section here, it's this one is locked. It's got the 1 screw in it. Otherwise, they would just a 1/4 but half a turn, 1/4 of a turn, then they come apart, and the flight computer is inside there with some padding to keep it safe during the recovery phase. The flight computer is currently this board here. I don't remember the exact dimensions, but I think it's 47 this way and maybe 60 or 70 millimeters that way. But anyway, it's packed pretty tight with components. They're all through the hole, so there's no surface mount issues going on with that. And this thing flies with a 850 milliamp hour, 1-cell lithium battery that's good for about 8 hours of continual use. I got one in here to keep in my fireproof bag. This is would be the battery it would fly with, or one similar to it. There's several different ones that we're trying. See which one we want to go with, but this is most likely in battery. And they can be as small as a flown mini with this. This is a 600 milliamp hour or 500 milliamp hour, and it's just a smaller, lighter battery. It's easier to get in there, but they're all single cell. Then that gives a lot of reliability. You don't have to worry about a 9-volt being semi-discharged or anything. You charge those up the day before you go flying, they'll be good for the entire day of flying. Now the 850 you could leave it on, not that you would, but you could leave it on. Once the flight computer completes its flight, when it gets back down to 50 feet, it goes to sleep and turns itself off until you turn it back on. It saves all the data. And then so the ejection charge, which is standard for me, is this type igniter, where I'm sure you've seen these before. They're called, a lot of people call them E-matches. And just a good igniter with electricity through those 2 wires. And I put that inside like a paper, looks like a firecracker container, but the ends are little plastic cups that just push in there, friction fit, and so instead of exploding, it just pops the ends off, gases the tube, increases the pressure, and kicks off whatever you need kicked off of it. So we're getting kind of towards the end now. I make my own parachutes and my own protective Nomex thing. All these things, this cloth is available on Amazon. I ain't got a parachute because the last one I made is in this rocket behind me here. I follow Rotary Rocketry's video. I've learned a lot from George on his videos. His dimensions, the way to get the dimensions right for an 8-sided parachute. But I do not do the sewing. It's again, it don't really matter where they're sewed or not if they're hanging on the top of a tree. So I want one that'll last, 10, 15 flights is all I'm worried about in these particular rockets. Maybe even less than that. So then in the future, now that we're wrapping this one up, in the future what I'm going to do is go through this thing. This is a copy of a 24 millimeter casing that I make. It's made out of 1-inch OD aluminum tube. And I modified the rockets to, and I should have brought one here. Let me go get one. We'll stop here and I'll go get it. Okay. This is a BT-70 research rocket that's been used to develop this flight computer, which required a lot of flights, and I'll either fly it with a sugar load or a HTTB APC load that I've made the fuel for. Or it will be flown with I just bought some Redline from the Aerotex sister company, and so that's pretty much what I'm flying now. That it'll be sugar or Redline usually now, or the commercial E11-0, since I'm not worried about an ejection. It's taken care of by the flight computer. And so then, with this 1 inch, it's not going to fit in the standard 24 millimeter tube because it's bigger than that. And so what it has to be is a 29 millimeter tube. And these rockets they look rough because they've been put through hell and back. So you got the standard 29 for the 29 millimeter Aerotech style engine, and what I do is I make just a rolled up adapter. It's a couple rolls of paper stock. It's pretty stout. There's several ways of doing it. You know, this is one that's got a tube on the end of it to get it centered. And the main thing is to hold the rocket centered. So what happens is you take this engine. It's got a C-clip here on this end, and then retainer rings on the inside to hold the engine together. And then it's just inserted into this. It's a rather tight fit, and then this is inserted in there, and you get an engine that's securely mounted in the center position. I had to do that because it's a lot easier. The inside of this one is 0.87, and that's the same dimensions that the reload kits from Aerotech are. They're for a standard 24 millimeter casing and 24 by 40 casing. And so then this thing is machined out, which is, I don't have to machine the inside other than cut the grooves and cut the groove on the outside. And then of course, obviously cut the length to start with, and then powder coat it. Some are and some not. It's really, you know, just an appearance type thing. The good thing about this size tube is you can take the standard adapter, which adapts a 24 millimeter engine to a 29, and stick that in there, and you can get it in there right, not backwards. Stick that in there, and you can fly, you know, either Aerotech's 24 millimeter or ST's 24 millimeter. A lot of this is done during the dry season here with commercial engines, be it E11, I don't know why I say E11, E12-0. The ignition on this style engine, no matter what I put in it, because, you know, the reload cost about $4 a piece, counting the kit and the chemicals to make the fuel. So it's very easy to spend the same amount on an igniter. And I've not had good luck with igniters, even the commercial ones, lighting sugar sometimes. And that was probably due to that weak potassium nitrate. But anyway, I have found out that on a short engine such as that, well, the way it will be ignited is with one of these fuse igniters, which has got a nichrome wire in there that makes contact with a 2 millimeter fuse. And the 2 millimeter fuse, it ran up to the top of the engine where I use a little bit of a primer charge. It's not black powder, it's magnesium is substituted for the sulfur. So you get a burn instead of an explosion. And what I found out is with those small engines, invariably, this will overpower them. It'll be a good ignition source, but it overpowers the casings and then they'll blow the ends off of it. And so I had to stop using that and go with a more sedate igniting. A lot of people say you don't use the fuse in the engine. I've not noticed anything detrimental to using this fuse, and it's because the core is very short, and the fuse most of the time will not light the engine by itself. Even though it's burning up in the middle of it, it can and it will, but most of the time it will not. It has to have that little primer charge, which is just a few grains of that powder, potassium nitrate, charcoal, and magnesium. And the magnesium, of course, once you get it burning, you know, it's going to spew out metal particles that's going to embed itself into the core of the engine, and it lights right away. And it don't have an over pressure. So that's going to be coming in the future. I'm going to show how to make these. And I guess that about wraps up the series on building the Phoenix. Hope you've enjoyed it. Maybe you learned something. Maybe you learned some bad habits. I don't know. You've even heard me get animated and say maybe scrap it myself. But anyway, I've had fun doing it. And we'll see you on the next one when I start the 29mm engine build. And go through it in detail. Start with the machining, the cutting, and then the machining, and then the loading the propellant and the assembly. So until then, blue skies. See you later.